Good morning to everyone. My name is Dr. T. Vamshi Prasad. I'm working as the assistant professor in BVRIT in Narsapur, Department of Physics. Today topic is uh, dielectrics, that is the types of polarization. Last class we discussed about the dielectrics introduction and fundamentals of dielectrics. What is the dielectric constant? What is the relative dielectric permittivity? What is the electrical susceptibility? What is the electric flux density? So what is the relationship between the electric flux density, polarization and permittivity? And what are the basics of the dielectric material? What is the polarization? What is the physical significance of dielectric material? Last class we discussed about the some fundamental definitions of dielectric. Now today topic is the types of polarization due to the dielectric material. In previous class we discussed about the polarization is equal to the dipole moment per unit value. Okay. Now the importance of polarization is we are calculating here the polarizability is equal to induced dipole moment per unit value. Here we are calculating about the total polarization of dielectric material is equal to the electric polarization, ionic polarization, space charge polarization and orientation polarization. In this phenomenon, dielectrics are non-conducting or insulating material. It is having for very large energy band gap. When such material is kept under external electric field, the polarization will takes place. So polarization occurs due to the several atomic mechanism. When specimen is placed in DC electric field, polarization is due to the four types of processes. They are electric polarization, ionic polarization, orientation polarization and space charge polarization. We have to derive about the polarizability alpha is equal to mu by E. So here, first of all, what is the importance of electronic polarization? What is the relationship between the electronic polarizability versus induced dipole moment? So, what is the importance of polarization in dielectric material in the absence of applied external field in the presence of the electric field? In the same case, one more polarization is ionic polarization. In the ionic polarization also, we have to find out for ionic polarizability and also for induced ionic polarizability. The equation is alpha I is equal to induced dipole moment. We have to write for ionic induced dipole moment per unit electric field. In the same step, we have to calculate for polarizability of ionic polarization. Best example for ionic polarization is NaCl. We are taking for NaCl atom, that is NaCl. We are taking for one is the positive charge, one is the negative charge. So one positive charge, one negative charge separated some amount of distance d is called about the dipole moment. In the same similar category, we have to find out for what is the orientation polarization. So orientation polarization is also for the important aspect for the dielectric material. Last one is space charge polarization. In these four types of polarization, our aim is to calculate for induced dipole moment is equal to the alpha into electric field intensity. Here, induced dipole momentum increases, the strength of the electric field is also increases. So, induced dipole momentum is decreases, the strength of the electric field intensity is also decreases. Here, the term is said to be alpha. The polarizability is important for these four types of polarization process. Simple one, polarization is equal to the dipole moment per unit value. You can see the diagram. We are taking for different types of polarization. One is the electronic polarization, one more is the ionic polarization, one is the orientation polarization. The last one is space charge polarization. in this category, we can see here in the options of applied electric field intensity, the structure is like that. Once if you apply the external electric field intensity, the polarized atom will be changed into the unpolarized atom. See here, for example, we are taking for one positive charge, one negative charge. They separated by some amount of distance. The dipole is produced. Once if you apply the external electric field, the ionic orientation of the molecule will be changed. In this category, we have to find out first what is the importance of polarization mechanism in the electronic ionic orientation and space charge polarization. Coming to the next slide, see for example, electronic polarization, ionic polarization, orientation polarization. In these four types of polarization, the temperature is important factor. Why you are choosing about the temperature means the characterization of dielectric material mainly depends upon the frequency versus temperature. One more time I am repeating the point. The characterization of dielectric material mainly depends upon the frequency versus temperature. In this one, electronic polarizability and ionic polarizability mainly depends upon the temperature. Orientation polarization and space charge polarization mainly depends upon the dependent of temperature. How can we now about the independent and dependent mean? We have to derive about the equation for the electronic polarization due to the polarized atom into the unpolarized atom. You can see about the derivation part also. Now you can look at here, we are taking for various types of polarization process. In the see here, various polarization process occurring about the first one is electronic polarization, third one is the ionic polarization. Second one is the ionic polarization. Third one is about the orientation polarization. Fourth one is space charge polarization. In this diagram, for example, if you choose about the orientation polarization, the orientation polarization means when an electromagnetic wave of some frequency is applied to the polar molecule, such as water molecule, the water molecules are try to rotate from one equilibrium position to the another equilibrium position. Here its orientation will be changed. That means rotating from one equilibrium position to another equilibrium position. So that what happens here, we are taking for polar molecule. What is the importance of polar molecule here? Polar molecule having about the asymmetrical charge distribution. So the best example for polar molecule is it is having for the permanent dipole moment. In the permanent dipole moment, we are seeing about the water content molecule, that is H2O. Once if you apply the electromagnetic frequency related to the polar molecule, the water molecules are try to rotate from one equilibrium position to the another equilibrium position. So the rotational frequency of the water molecule, which is equal to the incoming frequency of the electromagnetic wave, there is a resonance is occurring. So here the content will be oriented. That means X position is changing into the Y position. Y position is changing into the Z position. Just like popcorn. Once if you heat about the popcorn in the material dielectric heating substance, the structure will be changed from one position to the another position. That's why we are saying here orientation of the molecule will be changed from one orientation to another orientation. Like that ionic polarization. In the ionic polarization also we are taking for one positive charge, one negative charge separated by some amount of distance. It is said to be dipole. So here the dipole is important. If it is non-dipole moment, the metal does not get heated. It is said to be non-polar molecule. Now if you look at the space charge polarization, the space charge polarization also we can see here positive charge, negative charge, positive and negative charges. You can see a positive charge, one negative charge and positive charge. All the atoms or molecules are arranged in a periodic arrangement. Once if you apply the external electric field, its spaces will be changed. Now you can see this is said to be completely negative one side, positive one side. That means the charges are slightly displaced from one end to the another end. That's why here we are every time choosing about the dipole moment. If it is dipole moment, we can easily calculate about the polarization. Now you can see about the electric polarization. So in this electric polarization, first we have to calculate for what is the induced dipole moment. Induced dipole moment is mainly depends upon the electric field of intensity. In that electric field of intensity, we are defining about the new parameter, that is about the polarizability, that is alpha E. This polarizability is mainly depends upon the electronic, ionic orientation and space charge polarization. So here induced dipole momentum is increases, electric field of intensity is also increases. Now you can see here, once when an electric field is applied to the atom, what happens? Positively charged nucleus displaces in the direction of the field and electron cloud in the opposite direction. We are taking here dielectric substance material. The dielectric substance material is when taking about the atom. When an electric field is applied to an atom, positively charged nucleus displaced in the direction of the field, electron cloud in the opposite direction. In this phenomena, the displacement will produce an electric field within the atom. The main parameter is material having about the dipole or not. If it is having for permanent dipole moment, we can easily calculate about the polarizability. So here the dipole moment is proportional to the magnitude of the field strength and is given by the in the form of the mathematical notation. Induced dipole momentum is directly proportional to the electric field of intensity, or we can write induced dipole momentum is equal to the one new parameter, that is alpha E. This alpha E into electric field intensity. So this alpha E is called about the electronic polarizability. Here one more parameter. What is the about the its frequency range? It electronic polarizability mainly occurs in the optical frequency nearly 10 power 15 Hz. It is independent of temperature. Very important point. It is the independent of temperature. Now I can see, coming to the next slide, what is the importance of the dipole momentum in electric polarization? So the process of producing electric dipole which are oriented along the field direction is called the polarization in dielectric material. Simply, polarization is equal to the dipole moment per unit value. The unit of dipole momentum is debye. I am taking here the process of producing electric dipoles which are oriented along the field direction is called about the polarization in dielectric material. I am taking here one atom that is placed in electric field. Here consider an atom placed inside an electric field. In this category, the center of positive charge is displaced along the applied field direction. Similarly, the center of negative charge is displaced in the opposite direction. One positive charge is slightly displaced along the applied field direction. The negative charge is displaced in the opposite direction. So what happens here? Automatically the dipole is produced. So you can see here the dipole is produced. Simply an equal magnitude of positive charge and negative charge separated by some amount of distance d, it is said to be dipole. So the displacement of positively charged nucleus and negatively electrons of atoms are in opposite direction. So now once if you apply the application of electric field, it results in electric polarization. In the mathematical notation, induced dipole momentum is denoted by the symbol is mu. The induced dipole momentum is directly proportional to the electric field intensity. So here induced dipole momentum is increased, electric field of intensity is also increases. We can see this is about the directly proportional to. Once if you remove about the directionality factor, we can write one new notation, that is about the constant parameter alpha E. This alpha is called about the electronic polarizability. The electronic polarizability is independent of temperature. That is about the main point for the electronic polarizability. Coming to the diagram here, I am taking about the electric field intensity and its direction. Now you can see here, if you increase about the electric field intensity from low level to the higher level, the polarized atom will be changed into the unpolarized atom. That means the displacement of the the displacement will be changed from one end to the another end. Now you can see here, it's electron energy level. If it is polarized, the energy level will be similar category. If electric field intensity will be increased from low level to higher energy level, its position is also from increasing from low energy to the higher energy. Here the energy is important. Okay, that energy is nothing but the electric field of intensity. If you apply about the very strong electric field, the polarized atom will be changed into the unpolarized atom. And that's why we are calculating for what is about the its polarizability. The polarizability is mainly depends upon the independent of temperature. See here, consider an atom that is electric field of intensity. The nucleus represented by plus Ze and electron is represented is minus Ze. I am taking here two parameter. One is the nucleus of charge plus Ze and electron cloud that is minus Ze of the atom having about the opposite charges. Here opposite charges, that means there is some force is acting upon the nucleus and electron cloud. That force is nothing but the Lorentz force. This is about the main point for the electronic polarization. Here consider a atom in an electric field of intensity. The nucleus of charge and electron cloud of the atom have opposite charges. Here some force is acting. Some force is acting. What is that force? That force is namely it is said to be Lorentz force. Subsequently, nucleus moves in the direction and electron cloud in the opposite direction. Our aim is we are taking about the equal magnitude of charges. One charge is nucleus and that charge is electron cloud. That electron cloud is represented by minus Ze. So here see, subsequently nucleus moves in the direction of the field and electron cloud in opposite direction. So here the electron cloud and nucleus slightly displaced from their normal position. That's why here once the atom is displaced or shifted from their normal position, here one more force is acting. That force is due to the force of attraction between the nucleus and electron cloud. There is a Coulomb force is developed between the electron and nucleus. See here, attractive force between them is created and separation continues until Coulomb force is balanced by with the Lorentz force. Here two forces are acting. One force is Lorentz force, another force is due to the force of attraction between the electron cloud and nucleus. Coulomb force is developed. According to the thermal equilibrium condition, the two forces are namely equal. One force is Lorentz force, another force is Coulomb force. Now we can see about the mathematical expression point of view. Lorentz force is developed due to the electric field of intensity, the nucleus and electron cloud, and also the Coulomb force is shifted due to the electron cloud and nucleus. According to the thermal equilibrium condition, we are taking about the Coulomb force is equal to the Lorentz force. In the diagram you can see here, we are taking about the sphere of electrical charge, that is Ze. The nucleus is this one. The nucleus is slightly displaced or shifted from their normal position. See here, once if you apply the external field of intensity, this is about the virginal position. The nucleus slightly shifted from their normal position. Now you can see here in this diagram, we are taking for one positive charge, one negative charge, separated by some amount of distance. Dipole is formed. Here what is x here? X it is said to be the displacement of the atom. It is slightly displaced or shifted from their normal position. So in the derivation part, our aim is to calculate for electronic polarizability and also for induced electronic polarization. We have to find out for in the mathematical expression point of view, polarizability alpha. Here see in the mathematical expression, electronic polarizability is equal to the mu E divided by E. we have to find out what is the electronic polarization of the atom or molecule. The mathematical point of view, you can see here, consider the nucleus of charge Zg surrounded by electron cloud charge minus Zd distributed in the sphere of radius r. In the diagram you can see here, in the absence of external electric field, what is the structure? Once if you apply the presence of field, how the nucleus of charge is displaced in the presence of field. See, a figure 2 represents about the displacement of nucleus and electron cloud. We assume that the negative charge in the cloud uniformly distributed over a sphere of radius r. We are taking about the sphere of radius r, and spherical shape does not change about for the convenience position. It is slightly displaced. In the previous diagram also, we can see about the equilibrium position to the how the atom will be shifted from the original position. Coming to the derivation point, we can see here charge Zg, electron cloud minus Zd, the sphere of radius r. X is the displacement. X is about the displacement. In the mathematical expression point of view, here when electric field is applied, how the position will be changed. In the derivation point of view, we have to write about the charge density. The charge density is mainly depends upon the cloud of charge and also about the sphere. We are taking about the sphere of the charge. Our sphere, we can write about the volume. The volume of the sphere is 4 by 3 pi r cube. We can see here. The charge density is given by rho is equal to minus Ze by 4 by 3 pi r cube. R, it is said to be the radius of the sphere. So here, when an external field of intensity is applied, the nucleus and electron experiences the two forces. One is about the Lorentz force in the opposite direction. See here, nucleus and electron experience about the Lorentz forces in opposite direction. So that hence the electron cloud are pulled apart. The Coulomb force developed between them, which tends to the opposite to the displacement. Or displacement, it is said to be x here. That is about the mathematical expression point of view, right for x here. Okay, here two forces are there. One is about the Lorentz force, one is about the Coulomb force. I am taking about the two forces are, one for the Lorentz force, Coulomb forces are equal and opposite. I am taking about the equilibrium is reached due to the new equilibrium position. Fl, one is about the Coulomb force, Fc, one for the Lorentz force, Fl. This equation is valid only for the equilibrium condition. Here, when Lorentz and Coulomb forces are equal and opposite, equilibrium is reached. So that I am defining about the new parameter, that is x. X is the displacement of the electron cloud. In the mathematical part of equation, I am writing here Lorentz force is equal to the minus Ze into electric field of intensity. That means why negative symbol will came here? The nucleus and electron experiences the Lorentz forces in opposite direction. In terms of force, we have to write for charge into applied field. Lorentz force equation is okay. How to find out about the Coulomb force? The Coulomb force is the about the toughest job here. Lorentz force, we are taking about the opposite direction. The Coulomb force is the taking about the force of attraction between the nucleus and electron. So here Coulomb force can be written as charge Ze into charge enclosed in the sphere of radius x divided by 4 pi epsilon naught into x square. First, we have to find out for what is the charge enclosed in the sphere of radius x. In the mathematical notation, you can see here Coulomb force is equal to charge into charge enclosed in the sphere of radius x divided by 4 pi epsilon naught x square. First, we have to find out for what is the charge enclosed in the sphere. The charge enclosed in the sphere can be written as volume of the sphere multiplied by charge density. You can see here volume of the sphere, we can already know it is said to be 4 by 3 pi x cube. Charge density, the charge density is defined by the parameter is rho. See, this is for the equation number 2. Previously, we have written about the equation number 1, that is about the charge density. So substitute equation 1 in equation 2 and simplify. The charge enclosed in the sphere of radius x is equal to, we are taking about the 4 by 3 pi x cube into, what is rho? Rho it is said to be charge density. The charge density, you can see about the mathematical equation form, minus ZA divided by 4 by 3 pi r cube. You can simplify this equation. We will get about the exact equation for the charge enclosed in the sphere of radius x is equal to minus ZE into x cube divided by r cube. Capital R. Capital R is said to be radius of the sphere. Okay. Now you can see Coulomb force. Already we defined about the Coulomb force in the equation. ZE into charge enclosed in the sphere of radius x equal to divided by 4 pi epsilon naught x square. What is epsilon here? Epsilon is said to be dielectric permittivity, or we can say it is about the dielectric constant. Okay. X is about the displacement. This is for the equation number 3. Now we can substitute in this formula. Coulomb force is equal to charge ZE. We can find out about the charge enclosed in the sphere of radius. This is radiation. Charge enclosed in the sphere of radius, that is x equal to, you can see the equation minus ZE x cube divided by capital R cube divided by 4 pi epsilon naught x square. Substitute this formula, you can simplify. We will get about the exact Coulomb force equation, that is minus z square e square x divided by 4 pi epsilon naught x cube. This is about the Coulomb force equation. Now, what is our aim? Our aim is to find out for electronic polarizability due to the atom, right? According to the thermal equilibrium position or thermal equilibrium condition, the two forces are namely equal. One is the Lorentz force, one is about the Coulomb force. The Lorentz force is defined by the equation in this way. You can see here, Coulomb force is defined by the equation in this way. You can see here, negative, negative. In the Lorentz force also, we previously defined about the negative symbol. That is about the opposite direction. Now you can see here, negative, negative get cancelled. We can write about the electric field of intensity E is equal to, you can see here, square, square gets cancelled. You will get about the ZEX divided by 4 pi epsilon naught into capital R cube. Now we can write about the displacement, that is x. We can find out about the x, right? So x can be written as, do it here, cross multiplication. We will get about the exact equation for the electronic polarizability. So here x is the applied field constituting about the induced dipole moment. So here we will get one equation, that is about the x, that is displacement under the applied electric field. We are taking about the two charges, one for the positive charge, negative charge, separated by some amount of distance x under the applied electric field constituting about the induced dipole, induced electric dipole. Our aim is, first we have to find out about the dipole momentum is forming or not. Once if it is dipole momentum is forming, it is said to be permanent dipole moment. The metal is said to be polar molecule. So here, under the applied field constituting about the induced electric dipole moment. Coming to the next slide, you can see here, induced dipole momentum can be written as ZE into X. Therefore, electronic induced dipole moment. Here the parameter notation is very, very important. Every time we have to write for mu E. Mu E is known as electronic induced dipole moment. So electronic induced dipole moment can be written as charge into displacement. Charge can be written as ZE in the equation form multiplied by, what is our displacement? Displacement, this is about the equation. Now we can simplify this equation. ZE gets cancelled. We will get 4 pi epsilon into capital R cube into electric field of intensity. Okay. Now you can see here, electronic induced dipole momentum is directly proportional to the electric field of intensity. In the mathematical expression point of view, I am defining about the new parameter, that is alpha E. You can see it. Compare this equation, I am defining about the new parameter, that is alpha E. Alpha E is called about the electronic polarizability. That is about the important for the derivation of electronic polarizability. Here in this equation, this is the induced dipole moment. E is the electric field intensity. Alpha E, alpha E. Alpha E is called polarizability. Which type of polarizability? Electronic polarizability. So, induced dipole momentum is increased. That means the strength of the electric field is increases. The induced dipole momentum is also increases. That is about the confusion for the electric polarization. So, here alpha E is equal to, we can write mu E divided by capital E. This is about the polarizability of electronic polarization. See here, alpha E is directly proportional to capital R cube. What is capital R? Capital R is said to be square of the radius. So the dipole moment per unit volume is called electronic polarization. It is independent of temperature. Okay, this is about the derivation part for the electronic polarizability. Coming to the next slide, orientation polarization. In the previous slide, we discussed about the electronic polarization. The similar category, another type of polarization is orientation polarization. The name only there, orientation. Orientation means the molecules are tried to rotate from one equilibrium position to the another equilibrium position. That is said to be orientation polarization. The best example is water molecule, that is H2O. Why you are choosing about the water molecule is it is the permanent dipole moment. Okay, material which possesses asymmetrical charge distribution, it is said to be polar molecule. Polar molecule having the permanent dipole moment. Best example is water contain H2O. The water molecules are try to rotate from one position to the another position. We can say it is one equilibrium position to the another equilibrium position. That's why it is said to be orientation polarization. In the absence of electric field, what is the orientation polarization? In the presence of external electric field of intensity, what is the orientation polarization? Our aim is the molecule having the permanent dipole momentum is permanent dipole momentum or not. If it is permanent dipole momentum, next what is the its content? The orientation will be changed or not. So dipolar system is one in which the dipoles are able to rotate. You can see here, able to rotate freely without an external field. The dipoles are oriented at random such that the system as a whole will have very minimal or dipole moment. Dipole momentum is equal to the, we can see a dipole moment. Polarization is equal to dipole moment divided by volume. It mainly depends upon the material content. When an external field is applied, it will exert a torque on each dipole and orient the dipole in the direction of the field. On the other hand, this order effect is the field will be countered continuously by the thermal motion of the dipole. It mainly depends upon the temperature also. That's why the interaction of electrical energy with matter is determined by the electromagnetic properties of the material. On a microscopic scale, under the steady state condition, these properties are conventionally described by the permittivity and permittivity of the material. The characterization of dielectric material include the measurement of complex permittivity as a function of frequency at a given temperature or as a function of temperature at a given frequency. That's why types of polarization content, it mainly depends upon the temperature. Temperature is also important aspect for the dielectric material. That's why here equilibrium will reach about the different dipole will make it to 0 to pi radian. The structure, the orientation will be changed from 0 to 90 or 90 to 180. That is, we can see here 0 to 180 with the field direction resulting at net polarization in the direction of the field. We can see here one positive charge, negative charge, electric field is applied. The dipole momentum will be in the different direction. This side, this positive charge will be one direction, negative charge will be another direction. So here in the orientation of polarization, it is independent of temperature. Now you can see here in the orientation polarization, the molecule will be rotated, that is displaced, orientation, rotated or oriented, or the structure will be slightly changed. That's why it is said to be, it is independent of temperature. That is about the main point here. With increase of temperature, thermal energy tends to be randomized about the alignment. The dipoles are alignment will be important here. So the orientation polarization is mainly depends upon the temperature. Now you can see here P naught, the orientation polarization is inversely proportional to 1 by T. K, it is said to be Boltzmann constant. What is N here? N, it is said to be, there are N number of dipoles in the material. E, it is said to be electric field of intensity. That's why the orientation polarizability denoted by new parameter, that is alpha naught. Alpha naught is directly proportional to induced dipole momentum and inversely proportional to 1 by T. So, orientation polarization inversely proportional to absolute temperature of the material. That's why P, average polarization, Kb, it is said to be, K suffix B, it is said to be Boltzmann constant. T, temperature, N is the number of dipole moment per unit volume. Okay, this is the important for the orientation polarization. Okay, next class we can discuss about the what is the ionic polarizability and space charge polarization. So the total polarization alpha E alpha can be calculated as alpha E plus alpha naught plus alpha I plus alpha S. So induced dipole momentum mu is equal to alpha E. So induced dipole momentum mu equal to alpha can be written as summation of alpha E electronic polarization, alpha I for ionic polarization, alpha naught for phase charge polarization, orientation polarization, alpha S for polarization into external electric field. So what is our alpha E equation? Alpha E is equal to 4 pi epsilon naught into capital R cube. This is about the alpha E equation. What is our alpha naught equation? Mu square divided by 3kt. Substitute here, we can find out about the induced dipole momentum of electric polarization. The next slide, we can discuss about the ionic polarization and space charge polarization, and also for the uh, internal field of a dielectric material, and also for the Clausius-Mosotty relation. Okay, this is about the types of polarization for electronic and orientation polarization. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.